more descriptive, no calculations, actually the next two parts. So we might even start part 6. I kid about going fast. You know, if I start, I've told you guys before, like if I start babbling off 100 miles an hour and too fast for you guys to write things down, or if you have a question, ask, okay? But we'll probably go ahead and we'll do part 7 and probably start part 8. No calculations. Need a calculator for this stuff. So this is where we get to just kind of add to what we've been talking about. We're going to look at some structures and kind of consider polarity as we go. There's different types of structures. You guys did Lewis structures, and Lewis structures kind of the most of the ones I'm going to list up here, I think on this slide anyway. It's got the most detail. Make Lewis structure, you see how the atoms are bonded, and you see the pot of valence electrons all entirely distributed. That means you get lone pair electrons. Cuccoli structures, you're going to see no lone pair electrons there, which to me, and we've talked about this, without the lone pair electrons, you can't know the orbital hybridization, so you can't know the shape of the molecule. So these are a little limited, okay? And then there's, to me, a subtle difference between these two. Structural formulas will show, let's see, the sigma bond skeleton, so it's the primary bond. It'll show you kind of how the atoms are connected, but if there's a double bond, it may not show up in the structural formula. Semi-structural formula will show you the sigma bond, may not show the sigma bond, but from the semi, and I'll go show you some examples of these, but from this particular formula, you should be able to kind of know how they're stuck together. I feel like we're losing more and more detail here. So the condensed structural formula shows, and you've seen these before, I know you have, shows all the atoms on one line. And then this is the weirdness, the line formula, and it's just, I have to show you what it looks like. But the line formula is all about lines, and to me, well, I guess it can work. I'll show you. The line formulas are interesting. We've talked about these two types of formulas before. The empirical formula is like a reduced, potentially molecular formula. Molecular formula is the real deal. If you can divide all of the subscripts by a whole number, you can reduce it to empirical formula. Sometimes molecular formulas are empirical formulas. So here we go. This is the cuccoli structure. And actually it also happens to be a Lewis structure because there's no lone pairs here. But you can see the sigma bond between the carbons and hydrogens. This would be for that same, so let's see what we got here. We got 4 carbons and only hydrogen, all single bonds. And this is what we call butane. Bute is 4. So this is butane. Showing butane 2 other ways looks like this. So notice it's the same information, but a little different. So you have to be able to kind of think of this. This is what we call actually a methyl group as being this, and these two as being these two, and this as being this. So it all works out. This one's a little more condensed. It's kind of like a mathematical thing, basically taking 2 of those, putting them together and saying CH2 quantity 2. Okay, so they're all butanes. Oh, here's the line formula. Check this out. This is butane 2. So if your line doesn't have any oxygens or anything, it's only carbon and hydrogens. Keep that in mind. So all we have are carbon and hydrogens. At the beginning of the line, you have a carbon, and at the end of the line, you have a carbon. So I'm going to put carbon, carbon, and then wherever there's vertices, we have carbons. Carbon, carbon, carbon. So there's my 4 carbon chains of my butane. The other thing about line formulas then, and they will show you double bonds. Line formulas will show you double bonds. Each carbon wants to reach out 4 times, and it's not shown, but what it's reaching to are hydrogens. Like, really? Really? So I look at this guy, and he's only singly bonded to another carbon. Like, this is the sigma bond between those 2 carbons. So in order to give him 4, I'm going to have to give him, connected to 4 things, I need to add 3 hydrogens. So where I have the dashes, those are hydrogens. Down here, it's connected to 2 other carbons. It wants to reach out 4 times. So I need to give it 2 hydrogens. That would be 2 hydrogens here, 2 hydrogens here, and 3 hydrogens there. So that's just the way, that's the way. And we kind of talked about the whole spatial thing the other day, and we dealt with a diol. And spatially, this whole zigzagging is kind of trying to show you a little bit the tetrahedral shape that's going with geometry with each of those carbons, because it's sp3 orbital hybridized. So in space, and we have actually what's called free rotation on those. Any single bond has free rotation. So anyway. So again, these are all butane, the C2H, whatever it is, C4. All right, here's another one. This would be, this is a semi-structural formula. All right. Notice that they're not taking the time to go ahead and show these 3 hydrogens are distributed around the carbon. This hydrogen is coming up this carbon, etc. We'll be talking more a little bit about naming, just kind of touching on maybe. But in order to name it, what you do is you come up with your longest carbon chain. So it's like playing games. And so I have 1, 2, 3, 4, 5, 6. I actually have 6 carbons. If I say, no, I'm going to turn here, I'll still get 6. Turn here, I'll get 6. What if instead of going this way, I went this way, I'd still end up with 6. So 6 is our longest. So actually the prefix, I'll go ahead and put these up on the board for you. I said the prefix for number of carbons, prefix for 4, I said was but. Prefix for 5 is pent. Prefix for 6 is hex. So actually, we have a type of what we call a hexane here. And then to really kind of get down the nitty-gritty, we have to say where it branches, but I think I'll hold that for another time, just a minute, momentarily. So these actually are semi-structural formulas that give the same information. Let's see if we can find it. So this right here, this CH goes with this CH, and it's saying that there are 2 CH3s, or 2 methyl groups branching off. These 2 CH2s, this carbon is there, and it's showing that we have 3 methyl groups branching off. So they're the same thing. All right, different structure. Now, in this structure, it gets a little exciting. We'll be talking about functional groups. And so this is an example of a what we call a carboxylic acid. Carboxylic acids are characterized by a carbon double bond oxygen. That same carbon has an OH group. But this would be the Kukule structure. Now, the Kukule, I don't know if I'm pronouncing that right, the Kukule structure, remember, it doesn't show lone pair electrons like the Lewis structure. So if you're like, oh, Mrs. Snipes, that looks wrong. Well, it's not wrong, but you figure in order to have a complete octet, you've got that oxygen, which is quite common to have 2 lone pair electrons around it. So anyway, Kukule structure, carboxylic acid. This would be the same molecule, but in a structural formula, and to me they look very similar. They're not kind of showing the hydrogens kicking off the carbon, 3 hydrogens kicking off that carbon. It shows what we call the carbon chain, shows where your carbon double bond oxygen, single bond OH are. And one of the things we've talked about, and it's coming up in the slides, anytime you see this, you should think hydrogen bonding. Now I'm going to warn you, or I tried to kind of say this, but if you get hydrogen bonding in a big, humongous molecule, you only have one tiny hydrogen bonding. Of course, that's very polar. And if this is like a non-polar, then you might end up with kind of not a very polar situation. But, okay. So this would be the line formula of the same compound. Again, we have carbon here, carbon here, carbon here. Okay, so those are our 3 carbon chain. Line formulas aren't bad. They just take a little getting used to. Okay, so Hydrocarbons, no kidding, are compounds that contain only hydrogen and carbon in them. And we have some kind of different flavors of hydrocarbons, including alkanes that we were talking about, like the hexane and the butane. The thing that alkanes have is they're all single bonds, no double bonds anywhere. Alkenes have one double bond somewhere, and alkynes have one triple bond somewhere. A benzene is a benzene ring. I'll show you that in a minute. My point here is if you have a hydrocarbon, one carbon and hydrogen, and you're looking for the polarity or an even distribution of electrons, you're like, well, the carbon is more electronegative, but not a whole lot. That 0.4 is not a whole lot. So we generally say hydrocarbons are non-polar. They're generally called non-polar. Now, there is can we induce a dipole on it? Well, the bigger they are, the harder they fall. No. The bigger they are, the more likely you are to have a momentarily lapse of partial negatives and partial positives. So it increases its ability to induce a dipole on it. Okay. So alkanes. Now usually if I think of it, I give this to students at this time. So my maiden name was Newton. Of course, my first name's Elizabeth. And so this is a copy of the inside of my organic chemistry book. And if you get an organic chemistry book, it's going to have like a sheet that kind of shows some kind of different types of what we call functional groups. But alkanes, if you find alkanes on here, alkanes alphabetical. There it goes. Okay, alkane, it just says R-H, where the R can be any sort of carbon hydrogen thing. Okay, so alkanes, like I said, they just have carbon and hydrogen. So R is a chain. R is a carbon hydrogen. I get it. R is an alkane. So yeah. So let me go ahead and add to my little number of carbons. Let's see, 2, 1. So here we have meth, F, pro. And actually, you know how we did like nomenclature in lab, like nomenclature of ionic compounds? Well, in organic chemistry, they definitely kind of do some nomenclature too. But the fact that it ends in A-N-E means it's an alkane. And actually, the last column in the sheet I gave you says how you can recognize the name of the compound. It will end in A-N-E. All single bonds. Here we have butane. Bute means 4. You can see the 4 carbons there. You know it's all singly bonded. Not sure, but you do know because you have the right number of hydrogens to kind of saturate those carbons. This is another type of alkane. A little bit ago, actually we call this, I picked out, it's a different one. If I look for the longest number of carbons I can come up with, carbon chain, I'm looking at 6, so that makes it a hexane. Okay, I go 1, 2, actually I'm going to do it the other way around. You number them to get the lowest numbers here, and the numbers here are identifying what carbon they're on. So if I number it from this direction, 1, 2, 3, 4, 5, 6, I would get like 4 and 5 would be where they're at, and I don't want to do that. So that's why instead you number it 1, 2, 3, 4, 5, 6. So that's why my branching with what we call methyl groups, and here's where a di comes in. Di means 2. So I have 2 methyl groups. Where are they branching? They're branching at carbons 2 and carbons 3. So anyway, it looks weird. You're like, well, shouldn't that be some sort of octane? Because you have 8 carbons, but the longest carbon chain we have is 6, and it branches at positions 2 and 3. What does it branch with? Cute little methyl groups. So. But bottom line with regard to polarity, you're like, non-polar, but it's getting pretty big, so you can induce a dipole on this one more than you can induce a dipole on that one. So we're on the same page. Which would have the higher boiling point temperature? The top one or the lower one? Think the lower one too? Yes. You got it. So now if you look at alkenes, all it does is it has two R's. I mean R2 and the, how do I say this? The R2s would be alkane groups, and they wouldn't necessarily be the same. An alkene, all it is a hydrocarbon with double bond in it. And we have to say where the double bond is, if there are options. Prop meaning three carbons, ene meaning it's got a double bond somewhere. Here's one with 5 carbons, is the longest chain. 1, 2, 3, 4, 5. Okay, and we need to go ahead and tell 2 things here. So it's going to be a type of pentene, but we need to say where the double bond is. In this case, it's carbon 2 to 3, and then we also need to say where the branching is, and it's also on carbon 2. So that's why it's 2-methyl-2-pentene. My point here is to be non-polar. That's an alkene. Here's another one for you. So if we try to kind of see what sort of carbon chain we have, 1, 2, 3, 4. So we have 4 carbons. By the way, I've been talking about kind of free rotation. I think I mentioned this in Gen Chem 1. We can think of free rotation around single bonds, but when you have a double bond, not so much. In fact, it's rigid, it's set there. So with that in mind, with this kind of configuration, we end up with this is rigid, so actually, how do I say this? It makes a difference. We have potential rearrangements, potential for isomers. So this particular isomer it's got a double bond, so that makes it an alkene. There's 4, so it makes it a butene. The double bond is on the second carbon, second and third. And the other option, actually, we'll be talking about this in maybe actually tomorrow. This is what we call a trans configuration instead of a cis configuration. I'm like a cheerleader, okay? So this is trans. It's like the methyl groups are opposite the double bond. Trans versus cis. They're on the same side of the double bond. They have different properties. We'll actually see that they have different melting point temperatures. So that's that. Aromatic means relatively volatile. I think of benzene ring. This is actually a benzene ring. The formula for a benzene ring is C6H6. And I think I talked about this in Chem 1. So those 6 carbons are actually arranged in a circle. Okay, carbon, 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 carbon. We talked about resonance structures in Chem 1. So I could make this a single bond. I can make this a single bond, this a double bond, single, double, single, double. That's actually in resonance with this other possibility where, I'm kind of keeping the carbons where they are, the same orientation. Instead of a double here, I could make it single. Make this double, single, double, single, double. And of course, those are my C6s. My H6s means like at the end of each one of these little lines is a hydrogen. But this is a benzene, and it's showing you the benzene ring. And so I probably did something like this where to go ahead and instead of drawing both of those potential resonance structures, which is kind of cool, we kind of say that those pi electrons are delocalized, and they kind of, I always think of a pop bottle. If you like lick your finger around a pop bottle, go, make that cool sound. So that's what I think of with that. Kind of showing you the delocalized pi electrons. So benzene is relatively reactive. So what will happen is we have all sorts of neat little things that can substitute for those hydrogens. So for instance, this is toluene. It just has a methyl group substituted where one of the hydrogens was. This is naphthalene, where actually it has 2 benzene rings that share a side. How cool is that? Okay, but those are all examples of hydrocarbons. All right. Well, organic chemistry is about hydrocarbons and hydrocarbons with oxygen. So let's kind of see what happens when you throw oxygen into your molecules. So we have some definite possibilities. Right off the bat, again, the effect can be diluted depending upon how much of the how big your alkane portion is. But anytime you see a structure with an oxygen, think polar. And if it's an oxygen-hydrogen, think hydrogen bonding. Okay. So if your oxygen is just kind of off by itself, then it's polar, but it doesn't hydrogen bond. Okay? So we have some different types of compounds then, and these are all listed on the sheet I gave you. We have alcohols, phenols, and carboxylic acids that are all listed here. So if we take a look, we can kind of break up hydrocarbons with oxygen into 2 groups. The first group will have an OH exposed, so it can hydrogen bond. This group right here, ethers, aldehydes, ketones, and esters. I get my esters and ethers mixed up. Why did they do that, right? But anyway, this sheet can kind of help clear it up. But those have oxygen, but it's not an oxygen and a hydrogen. So you won't, the oxygen is not bonded to a hydrogen. So you won't get any hydrogen bonding, but it will be polar. Okay, so alcohols, if we find them on the sheet, it just says ROH. That OH that makes an alcohol, sometimes, I think Chem 1 we talked about this, that actually is called, in general, a hydroxyl group. Kind of like, I've been kind of blabbing up here, kind of like CH3 is called a methyl group. So here we basically have an alkane, which is our R, OH, which makes an alcohol. The fact that there are only 2 carbons makes it an F, okay? So actually, you can kind of see on here, I'm calling it ethyl alcohol. Another name for that is ethanol. Ethanol means the same thing. Ends in OL. All right, so it can definitely hydrogen bond. Here we have an example of a diol. It's actually got 2 hydroxyl groups, and I bet you guys would catch on that, well, which one is going to be the higher boil or higher temperature, the first or the second one? The second one. Did you say the third one? Like there's not 3 out there, Daniel.
I know which one will boil easier for some reason.
This one will have a higher boiling point temperature because you have these 2 hydroxyl groups. Yep, it's very good. So that's called ethylene glycol. I don't have a good way to know that. This again, we have the benzene ring with an OH, we just call phenol. And here we have an example of, this is a carboxylic acid. This one down here. If you find it on that sheet, carboxylic, I probably butchered that acid. You can see it just has R, C, double bond O, single bond OH. So this is kind of fun. To me, if I was like on an assignment trying to wrestle with its polarity, I'll ask an informal question. Let's compare acetic acid with ethyl alcohol. Which one would have the stronger intermolecular bonds? And why? It's a double bond. Yeah, I think it would be stronger. I think because we got that extra electronegativity going on there, and hydrogen bonding. Very good. All right. So aldehydes, I get my aldehydes and ketones mixed up. Now we're switching gears to things that will not hydrogen bond in their pure state. We're looking at things that still have oxygen, so they would have a degree of polarity. Aldehydes have, are kind of on the end of the carbon chain. Aldehydes have the carbon that's doubly bonded to an oxygen, then half bond hydrogen. That's an aldehyde. And by the way, you see where the prop came from? Prop means 3 carbon chains. Then this is an example of a ketone. And the difference, like an aldehyde actually has it, like I said, you kind of have a hydrogen, it's on the terminal. Ketone, the double bond oxygen is kind of embedded somewhere in the carbon chain. So this is an aldehyde. Aldehyde, ketone. Did I ever tell you guys, I think I got a C plus and a B minus in my organic chemistry. It was like, give me the numbers, but like I got A's in my PChem, and so I don't know. I didn't like how the teacher taught it. He was the dean. Now I told you I get my ethers and esters mixed up. I'm thinking ester. Okay. This one is an ester. Wait. Yeah, answer. What makes it an ester is where you have the carbon double bond oxygen. It's also singly bonded within the carbon chain to there's an oxygen within the carbon chain. So I'm thinking ester. What's an ether? Oh, okay. Ethers don't have a double bond oxygen. There we go. There's my ether. That's an ether. Yeah. I guess I can. So an ester, I don't know how you memorize it, but an ester has not only does it have an oxygen kind of in the carbon chain, but it also that same oxygen, that same carbon that's bonded singly to an oxygen in the carbon chain also has a double bond oxygen. And ether, nope, we just got an oxygen in the chain. I like the name diethyl ether. And again, kind of like we've been talking about, can you see the F means 2? And it's, I don't know if this is really the correct name for it using the rules of naming, but we have ethyl, diethyl ether.
Did you go to one slide?
Back?
Yeah.
Like this one?
Yeah.
Yes. But it's a type of diol with di meaning 2. So yeah, the F meaning like 2 carbons here. Okay. And I think like if you take organic chemistry, they'll probably do a better job at doing the rules of naming things. In non-organic chemistry, like we have water is H2O, and I don't know. There's like some of these names that are listed on my slides may not be the final names, right? But they're more of a common name, like dihydrogen oxide, right? Would not be the common name. Cool. Well, here we go. If you look on my sheet under amines, you're going to see the element nitrogen. So amines have to have nitrogen in them. Now, nitrogen likes to reach out 3 times. So we actually have some options here. We can have nitrogen, I'll do it this way because I wasn't real thrilled about how my slides do this. We have primary, secondary, and tertiary ways that nitrogen reaches out to things. So here we go. Nitrogen reaching out 3 times, 3 times, 3 times. I'll make this primary. In primary, we just do this. We do a 1 with a little circle. This is secondary, 2 with a little circle. This is tertiary, 3 with a little circle. If it's primary, if, I'll do it this way, tertiary. Tertiary, I'm gonna put an R here, and I'm gonna put an R here, I'm gonna put an R here. Where, according to what we've been talking about, that's just some sort of alkane or some sort of something, blah, 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 blah. Okay? For secondary, and these R's can be different. Here, I'm gonna put an R, and an H. Aha. For primary, I can't remember how this was. I'm gonna put an R, an H, and an H. Okay? Sorry, it's kind of blending into each other. So there we go. Primary, secondary, and tertiary. So I guess if you go with 1, 2, and 3, the first case it's bonding to one blah 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 group. Second one is bonding to 2 blah 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 groups and a hydrogen. First one is 1 blah blah group, 2 hydrogens. Second one, 2 blah blah groups, 1 hydrogen, and the other one's 3 blah blah groups. But
so the R is just like, it can be kind of any one of those groups.
yeah, the R is, and I've been saying an alkane, but it doesn't have to be an alkane really. It can be anything. It's just the rest of the molecule. Yeah. But the cool thing about this, and actually that's kind of what this slide says, maybe this will make more sense. Do you see where it says can hydrogen bond? So these guys, let's see what that looks like. Sites for hydrogen bonding, da-da-da, da-da-da-da, primary. Sites for hydrogen bonding, da-da-da, secondary. Sites for hydrogen bonding, nothing. Got nothing. Okay? So can you see where, and I'm not real thrilled with how this, my slide is right now, but like the first one, the thing that makes it primary is it's got actually 2 hydrogen bonding sites. Okay. So the 2 hydrogen bonding sites is this. If we take this and kind of expand it, hydrogen, hydrogen. Oh, sorry, drat. I'm sorry, my bad. That's not a nitrogen. This one right here. Okay, we can expand it, hydrogen, hydrogen. That's where your 2 hydrogen bonds are. Here, we only have 1 hydrogen bond. Okay, and this guy, not a chance. This tertiary amine, no hydrogen bond at all. Let's look at this tertiary amine and see how they named it. They named it, the root is dimethylamine, I suppose. Here's amine, methyl, methyl, dimethylamine, and then it called it ethyl. So ethyl, dimethylamine, I don't know. I suppose I see it, but.
So like for the test, are we supposed to like, we're not supposed to know different?
No, you're not supposed to have to name them. No.
Okay.
But this is just, because I'm probably going to trick this a little bit. So you won't have to name them, but you will have to, if I give you the Lewis structure, which I will, be able to recognize that a tertiary amine, you don't have to call it a tertiary amine, you might have to know that. A tertiary amine is not going to hydrogen bond. Oh, so here's one for you. In fact, this might be a question coming up, I think. If we compare ethylamine with diethylamine, so ethylamine had, here we go, 2 hydrogen bonding sites, and dimethylamine only had 1 hydrogen bonding site. So which one has the strongest intermolecular bonds? The first one, ethylamine. Yep, ethylamine, exactly. Yep, exactly. Because with all the other things being the same, because they have like very similar molecular weights. All right, so here we go. Alcohols have that hydroxyl group, okay? Alcohols will have a higher boiling point temperatures, stronger intermolecular bonds compared to their alkane version. Alcohols will also be have stronger intermolecular bonds than comparable ethers. And if you're like, well, what's an ether? Well, let me take a look. An ether, remember, was that one that had the oxygen bonded in the carbon chain. If you have an alcohol, you have hydrogen bonding. If you have an ether, you just have polarity. You have dipole, dipole. What else? And I think you guys have kind of told me about this, that if you get bigger, the molecule gets larger, adding carbons actually increases your the induced dipole, the polarizability of it, and so your boiling point's going to increase. Part of the problem with this material is, so on a test or homework, you're going to just need to kind of focus on and write it down, convince yourself the consequences, like for instance, of having a higher strength, intermolecular bond strength. Well, that's going to make it boil, make it harder to boil. So keep your wits about you there. Not that you don't have your wits. We talked about branching before, and branching is kind of balling up. It makes it less polarizable. So if you make it less polarizable, then your intermolecular bonds are going to be wimpier and your boiling point is going to be less. So all of that stuff, kind of what we talked about before, is just kind of rehashing it in terms of kind of organic molecules. If you add hydroxyl groups, okay, like the 2 hydroxyl groups make it a diol, 3 hydroxyl groups makes it a triol. There are definitely some, and I'm bad with my biomolecules, but in nutrition, fatty fats or comes from fatty acids, I don't know. But triol is an important player in biomolecules. All right. We talked about like dissolves like. So if you're looking at an alcohol in water, you're like water is polar, okay, and alcohol is polar. But there's the catch, and this is kind of what I've been maybe alluding to. As you add more and more carbons to your alcohol, and I have a picture coming up, you're basically adding more and more non-polarness to your alcohol. So small alcohols, these guys, up to 3, small alcohols will dissolve in water. If you add more carbons, it's limited. If you add 4 carbons, so the thing about 4 carbons is there's different ways to arrange those 4 carbons. I'll kind of show you what I mean. You could have normal with these carbons, or you could do normal, like straight chain, like hot dog, or we could go ahead and ball them up, and that's the tert. You have a lot of branching. Carbon, 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 carbon. These are 2 different ones, sorry. But these are both, did I have, wait, I made that 5 carbons instead of 4. Let's see how we can do 4 carbons, make some branching. Here, there we go, this is tert. Carbon, 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 that's the 2. So if you ball them up, it's less polarizable. It makes it more like non-polar. So it's not going to, it's going to be more likely to dissolve in water. All right, as the number of carbons increase, the solubility of the alcohol decreases. So this is to kind of, well, I have a picture coming up. So these are kind of grouping, kind of synonymous compounds, showing you, the last column is showing you the solubility in water. Last column showing you the solubility in water. For instance, if we take this second set that I put up here, 2 carbons in all 3 of these cases. But the first case, we have 2 carbons with hydroxyl group. Is it soluble in water? Infinitely. Substitute, instead of hydroxyl group, put in a chlorine. Yes, it's still soluble. Go ahead and take off that chlorine, substitute a hydrogen. Not so much. Okay, like dissolves like. So alcohols would want to dissolve in water unless they get too big. So now we've got ahead and have 3 carbons instead of 2 carbons, and look at its solubility. Still infinitely. Here we go. Add 4 carbons, straight chain, which is indicated by the 1 in the 1-butanol, and it's less soluble. Okay. So this is what I said was coming up. Now, the colors here, like the color coding there, you see The phobic means fear of, philic means love of. So in hydro means water. So hydrophobic means doesn't like water. Hydrophilic means loves water. So the loves water, the hydrophilic part, is trying to highlight the hydroxyl group. So this is methanol, where the green is your carbon and your 3 hydrogens, and the red is your oxygen and your hydrogen, your hydroxyl group. So what happens when you add more carbon chains, this is adding, instead of 1 carbon, now it's got 5 carbons. So here we've got a much more, the word is phobic, meaning fear of, hydro meaning water. So now we have increased the water-hating phobic part, okay? And it makes the hydrophilic part less impressive, less driving the show. So that's why the pentanol is less soluble. So this actually is showing you some kind of dizzying things. You see the dots, those are intermolecular bonds. This is actually in its liquid state, almost looks like it's solid state, but it's liquid state. This is pure water, and down here is methanol, pure methanol actually. And kind of in between is what we've talked about with mixtures, where we have breaking of the intermolecular bonds with a solid state and forming new intermolecular bonds with molecules of the different types. So of course, water, hydrogen bond, that alcohol, methanol, hydrogen bond. So those dots are all hydrogen bonds. Polyhydroxy alcohols. I think we kind of talked about that. The more hydroxyl groups you get, the more soluble it will be. A carboxylic acid, it takes on this form where you have a carbon double bonded to an oxygen. That same carbon is singly bonded to a hydroxyl group. And we got all sorts of options. To me, I think we talked about this before, carboxylic acid will be more polar, stronger intermolecular bonds compared to an analogous just alcohol, because you have that extra double bond oxygen. We'll be talking more about solids and their transition to liquids. Melting point temperatures have they're not as melting point temperature transition, you know what I mean, are not as straightforward as boiling point temperatures. Carboxylic acids, it follows the same trend. The more carbons you have, the less likely it is to dissolve in water. 10 is kind of the cutoff for being soluble in water. Carboxylic acids would not only be soluble in water, but also in alcohols. Again, as we have more and more carbons, non-functional groups, then your molecule takes on a non-polar kind of slant. This was an example of actually a ketone. It's a ketone if you have something on, like, non-hydrogens on the other side of that carbon. If you have a hydrogen over there, that's going to be an aldehyde. What they both have in common is that double bond oxygen, like the slide says, partially negative, so generally polar. So it will dissolve in water, but not as much as its carboxylic acid. It will not. Let's see what we learned. Can hydrogen bond? Well, I guess it can. This says it can hydrogen bond with water, but when it's hydrogen bonding, it's not providing the OH group. It's using water's providing the OH group. I feel like that's all just the same. Amines, look for the nitrogen. It's somewhere in there. So we had our primary, secondary, and tertiary amines, and we kind of talked about how only the primary, secondary can hydrogen bond. Tertiary amines cannot hydrogen bond. Oh. So, and we kind of, you guys, I think, convinced me that the primary mean would have the highest boiling point because it has the most hydrogen bonding with itself compared to the secondary. Are we about done? Oh my gosh. I ran out of steam like 6 slides ago. So, yay.
I have a question.
Party, yes.
So like how we're talking about the carbons, right? It's the same atoms, right? But they're arranged differently.
These guys?
Yeah.
Yeah,
Like
this
what-
is like the, like normal, and this is tert.
What determines like how they arrange themselves?
Ooh, that's a good question. There,
Like out in like nature and stuff. Like,
yeah,
Like how does that?
the conditions that they're formed in, like I know in the lab, I'm pretty sure, and it feels like almost like fracking, where you can actually chop this off and move it over. So, it kind of be an energy thing.
Yeah, I was always like
Yeah,
wondering like how does it? Because you know you can have like a bunch of different like rearrangements of the same.
Yeah. Yeah, it's a condition thing. And I know that like our bodies, when we go to metabolize things, are looking for, it's almost like a key in a keyhole. Like certain things we're going to metabolize and certain things we're not. And they're like the same atoms, they're just rearranged differently.
It's so interesting.
I agree. I agree. So one of the things I want to hit tomorrow, and I might hit it right off the bat, was to talk about one of the things on this slide. It reminded me that you can get, it said, and I'll try to explain why this is, but I can get this to hydrogen bond, but not just hydrogen bond with itself. Because you figure that nitrogen's partially negative, and it can bump up against like a water molecule, and if it, I think this is right, if it's like with a water molecule getting the partial positive part of the hydrogen to this, that's actually called nitrogen bond, or excuse me, hydrogen bonding. But it's originating from the water molecule. Have a good day. You too.